In our last video, we derived the expression of electric potential at any point due to an electric dipole. And from that final expression, we derived the electric potential at the axial point of an electric dipole and then electric potential at the equatorial line of the electric dipole. But in this video, we will derive the expression of electric potential due to an electric dipole at any point on the axial line of the dipole. See, this is the required diagram. Here AB is an electric dipole having magnitude of either charge Q and the separation between the two charges is 12. And let P be any point on the axial line of the dipole at a distance r from the center O of the dipole. Now let us start the derivation. So let us consider an electric dipole having magnitude of either charge Q and the separation between them to L. Let P be any point, capital P, be any point on the axial line at a distance r smaller from the center O of the dipole. Here OP, that is the distance of the point P from the center of the dipole, is R. Length of the dipole, that is AB, is equal to 2L. Then this is O, center of the dipole. OA is equal to OB, this is equal to L. Then AP is equal to, see here AP is equal to AO plus OP. So this is equal to AO is equal to, or OA is equal to L and OP is equal to R. So this is L plus R. Similarly, BP is equal to OP minus OB. See in the diagram, BP length is equal to OP minus OB. So this is equal to R minus L. So now let us find the electric potential at P due to the minus Q charge. So electric potential at P, at the point P, due to the minus Q charge which is at A. That is, suppose electric potential at P due to the minus Q charge be V1. So this is equal to 1 by 4 pi epsilon naught. Here the charge is minus Q divided by distance of the charge minus Q from the observation point P, that is A P. So this can be written as minus 1 by 4 pi epsilon naught Q divided by AP is equal to L plus R. Write this as equation number 1. Now electric potential at P due to the plus Q charge that is V2 is equal to again 1 by 4 pi epsilon naught. Charge is Q plus Q divided by distance of the point P from the plus Q charge, that is B P. So this is equal to 1 by 4 pi epsilon naught Q divided by R minus L, because BP is equal to R minus L. So let us write this as equation number 2. As electric potential is a scalar quantity, so the net electric potential at P due to the plus Q charge and minus Q charge is the algebraic addition of these two potentials. So now let us write the electric potential at P. So the net electric potential at P due to the dipole. So that is only the simple addition, that is algebraic addition of V1 plus V2, because electric potential is a scalar quantity, so we can add them algebraically. So this is equal to, here V1 is equal to minus 1 by 4 pi epsilon naught Q divided by L plus R or R plus L plus 1 by 4 pi epsilon naught V2 is equal to 1 by 4 pi epsilon naught Q divided by R minus L. Let us take Q divided by 4 pi epsilon naught common. Q divided by 4 pi epsilon naught 1 divided by R minus L minus 1 divided by R plus L. So this is equal to Q by 4 pi epsilon naught R minus L into R plus L. This is R plus L minus R minus L. So this is equal to Q by 4 pi epsilon naught. Let us open the bracket. This is R plus L minus R minus plus L divided by, this is A minus B into A plus B, that is A square minus B square, R square minus L square. Okay. See, this R and this R will be cancelled out. So this is equal to Q divided by 4 pi epsilon naught into L plus L, this is 2L divided by R square minus L square. One by 4 pi epsilon naught. This is Q into 2L divided by R square minus L square. But we know that the magnitude of electric dipole moment is equal to the product of magnitude of either charge and the separation between them. So electric here Q into 2L is equal to magnitude of the electric dipole moment, that is small p. This is equal to magnitude. We know that the small p, that is electric dipole moment, is a vector quantity of electric dipole moment. So this implies V is equal to 1 by 4 pi epsilon naught P divided by R square minus L square. But for an ideal dipole, L or the separation between the two charges is very small, in comparison to that distance, that is 2L is very less than that of the R. So this implies L is also very less than R, or L square is also very less than R square. So now let us ignore that L square in this above equation. This is the equation number 3. Now neglecting L square from this above equation, we will get, this implies V is equal to 1 by 4 pi epsilon naught P divided by R square, and this is the final expression of electric dipole moment at any point on the axial line of a dipole. In our next video, we will derive the expression of the electric potential at any point on the equatorial line of a electric dipole. We already know that at the equatorial line electric potential is 0. But again we derive that expression in our next video.